So we given yeah, because this is related to the geometry, okay, on quizzes. So this is an isosceles triangle. Okay, with fixed parameter, with a parameter of, for example, 100 units. Okay. Yeah, given an isosceles triangle, can you express the area in terms of any of the variables? Okay, could be the base, could be side, could be the height. Let's use the height. Okay, just for in terms of h only. Can you try? Because the parameters are fixed. Okay. Okay. It's tough, right? It's not easy. Okay, so let's see. So right, this isosceles triangle. The base is a b, right? You write down the first equation. Okay, so b plus 2a equals 100. That's clear. Okay. Then the area is going to be half of 8b times h. You want to express area in terms of h, then you have to express b in terms of h. That's it, right? Sounds easy. So we just needed to express b in terms of h. Right? Then you're done, right? The question, how do you do that? Well, you haven't used this formula yet, right? So you look at the triangle. The half of b is here, right? And h is here. I have to express a in terms of b. So a is going to be 50 minus half of b, right? So if you are able to express half of b, then in terms of h, then you're done. So this is a right triangle, right? For right triangle, you can always, for the right triangle, you can apply the Pythagorean theory to this problem, right? So how to do that? H squared plus half of v squared equals 50 minus half of v squared. It's not too bad, right? Surprise. Yeah, then you just need to find half of v. That's all you need. Okay, so you get 50 squared minus twice of that, that's the 50b, plus half of b squared, right? Half of b squared cancels out. Right, then you have a 50b equals 50 squared minus h squared, and b is going to be 50b is 50 squared minus h squared divided by 50. Okay, then that's it. That you can put into the formula. What is b? B is a 50. Here's 50 squared minus h squared and h. Surprise? Not that. It's polynomial. Right. We just apply the Pythagorean theory to this triangle and the area formula. Okay. Then, if you have to minimize this function, then this is a polynomial. It's polynomial degree 3. The polynomial degree 3. If you draw the picture, right? When h is 50 is here. This is greater 0. This is a. That's h. When the h between 0 and 50, this is 0. So this is a kind of, I don't know. It looks like that somewhere. Okay, for h between 0 and 50, a is positive, and somewhere it has maximum value. Okay, so what is the largest possible area of this triangle? An isosceles triangle with a fixed parameter. What is the largest possible area? If I ask you this question, you can solve this problem, right? Because you can always make the height as small as possible, as large as possible. No, it cannot be too large because the parameter, look at this h, okay? The parameter is 100. So h is between 0 and 50. Yeah, because the two sides there, right? The parameter is 100. So h is smaller than the sum of two sides, and which is half of that, right? So which is going to be 50, yeah. So that's the value of h. Then you have a function here, right? And what is the maximum value of this triangle, right? Then you just find out the derivative. Okay, so I'm going to express it in the following: 100 and 50 square h minus h cubed, right? Then I differentiate. Right. All right, so the answer is, if I set this to be 0, h squared equals 50 square over 3. That implies h is going to be 50 over square 3. Okay, so when h equals 50 over square 3, this area, this triangle has a largest possible value. Okay, so when h squared, right? So the answer is 150, 50 square minus 3, because h squared is a 50 square, right? Wait a minute. Square root 3, yes. Square, confused. Oh, I plug into the the derivative. It should be the area. Okay, so that is going to be 150 square minus h square and h, right? So I'm going to rewrite. I'll calculate the area. Okay, so h square is going to be 50 square over 3, and this is the 50 square 3, right? So after you simplify it, you get 1/3. 1 minus 1/3 is 2. Okay, and then you lots of simplification going on. Okay, this is cancelled out. So it's 50 square over 3 square of 3. Okay, so this is the largest possible area you can get. Okay, so let's go back to the problem again. You are given an isosceles triangle with a fixed parameter. Find the largest possible area. Now, use a common sense, right? Largest possible area probably should be how does the triangle look like? The parameter is fixed. So the right triangle, this triangle should be kind of like a, four sides are equal, right? You call it equilateral triangle. That's my experience. Okay, if I do not put a restriction, this should be triangle. I think the circle should give you the largest possible area. Okay, suppose you have a 100 feet long fence, right? You're a farmer. You want to, you want to get increase some regions for the whatever garden for animals, right? You want to increase the largest possible area for the fixed fence. So your experience tells you this should be circle, okay? But if you think you have to use a rectangle, then you decide must be square. So all sides are equal. If it's triangle, must be equilateral triangle. Okay, that's the bit, because then this maximizes the area you can get. Okay. So if you are the builder trying to build square type of house, but you can design in much better way, people still, the house still attractive to the people. Then save your material cost. Okay, because the square, given the fixed parameters, the square gives the maximum large possible area. Okay, maybe from all sides doesn't look best, but inside you get the largest possible area. So you can design. I think. Well, for storage room, definitely should make a square instead, because we don't care about the how does it look like outside, right? Yeah. All right. Okay. Then there are many ways to express it. You have to change you have to express the area in terms of one variable. I decide this time in terms of h. So I get a polynomial, right? The polynomial in terms of h. Then I find the exact value of h so that the area has maximum value. But I still don't want to know. I don't need to know how does the triangle look like. I just want to find the largest possible area. Okay, so I get this answer, solve the problem. But I guess the triangle probably looks like a equilateral triangle. Okay, but I'm not going to prove this here. So this is a good. This is a interesting optimization problem. Yes. Hmm. How do I get 3? Which one? H square? Well, you see, A prime, okay, is going to this. So H square is going to 50 squared divided by 3. So if you take a radical, then you get 50 over square of 3. But you just need here, when you plug them into the area formula, you still have to get an H square here. H square is still 50 square over 3. So, okay, and the H, now you have to use 50 over square of 3. So that's the reason you have square of 3. Okay, but the 1 minus 1/3 is 2/3. That's why I got 2/3 here. Yeah. I guess the triangle must be equal to the triangle. I'm not going to prove that because the question, original question is, what is the largest possible area you can get? Okay. Yeah, I think more optimization problems. Yeah, sometimes if you're able to solve optimization problems, they'll save you some money. Okay. Suppose if you want to build you purchase some large lot, you are going to have your own business, and then you're going to ask company to build the storage rooms, right? In my opinion, you have to do some calculation because the cost for the wall, right? You want to maximize the area for each room. So how does the room look like? Of course, you have to say there must be rectangular shape. Well, that's okay, rectangular shape. Okay, then you have to figure out the dimension of each room. Okay, and probably save you $10,000, even $20,000. That's possible. If you don't do that computation, yeah, you have to spend more money. Okay, because in my opinion, who cares about this square type of storage room or rectangular storage room, right? Just as long as you can lock in and keep it safe, then fine. Okay. Okay, now so section 4.1 is the first section we step into integrals. We're going to study integrals. Okay, integrals. But the motivation to study integrals actually is at the very beginning is trying to find the area of certain region, right? And find the area of certain region. So the first, we'll have to define the region, right? Yeah, given us rectangle, right? And I was talking to a child, say, how can you compare two cakes, which one is large, right? And I give it two cakes that they're all rectangular shape. And you have to decide which one. You cannot just look at, oh, this looks like, sometimes harder to tell, like how to measure it, right? So we introduce a so-called area. So if this is A, that's a B, the area tells you how large of this cake. So A times B. And the geometric meaning of A times B, if you divide them into, that tells you how many, for example, how many units square there. If this is a 1, 2, 3, 1, 2, 3, 4, right? And this is 3, this is 4. 3 times 4 is equal to 12. The geometric meaning of 12 is you have 12 pieces there. Okay, so that's the reason the area, the product, two sides really tells you how large of this this rectangle. Okay, yeah, because just count how many pieces, square units, right? Square unit, unit square is the basic unit, right? So you just count how many pieces, right? 12 pieces. Okay, so that's the reason you just do the multiplication, gives you how large of this rectangle. All right, now the problem is if the region is irregular, sometimes even just a circle, right? How can we find the area? Okay, so we here's a question. So we make it a little bit simpler, but it's still complicated. Suppose the top one is a curve, okay, but the bottom one is a straight line. Okay, this is a greater than or equal to 0. X is greater than A, less than B. How can I find the area of this region? Okay, how can we find the area of this region? Okay, and the special case is the up semicircle. I just said that, the special case. This is general case, the special case. The special case is an up semicircle. So if you're able to find the area up semicircle, then you find the area of the circle, right? So this is y equals r squared minus x squared. X is between r, right? So that's a special case. That's a motivation, So more general, right? We want to find the area of the region and this graph. If the graph is given by square root r squared minus x squared, and that region is given a semicircle, okay? That's a special case. So the idea is that we're going to cut this region into many slices, okay? Into many slices. So you partition the interval, okay? Not necessarily equal size. So A is going to be x0 less than x1 less than A, okay? That's just an arbitrary partition. Then you look at the i's term. So this is xi minus 1, this is xi. And I'm going to estimate this area. What I'm going to do is I pick an arbitrary point, we call it xi star, and look at the value of this. So you get a rectangle of, and then you look at the area of this rectangle. This rectangle is going to be the base, okay? It's going to be, let me denote x delta xi is xi minus 1, okay? So this is the size of subinterval. So the area AI is going to be, this is going to be approximate by the height of the rectangle times delta xi. The height is just the value of the function at some point, arbitrary point inside the interval. Okay. So what I'm going to do is, this is xi minus 1, this is xi, then I pick arbitrary point between those 2 points, then I take the value, this tells us the height. And I draw the line, horizontal line, so I get a rectangle. But this rectangle almost occupies the region, or covers the region and the curve. Okay. So the total area is going to be A, right? It's going to be sum of area of those regions, but each of them approximated by this. Okay. So in 1850, okay, in 1850, Riemann, okay, 1950, no, 1850, okay, that's a long time ago, 150 years ago. It's not too far, right? And then he says that, well, you know, the error, we want to see whether the error is large or not, right? So otherwise, it doesn't matter. You know, there's so many small regions you get to estimate. So that if the error for each small region, okay, if it's small, but if you add them together, maybe large, then it's not good, right? So I want to make sure those two, yeah, I want to make sure this is indeed very close to the area of the region. Okay, so Riemann says that don't worry about it. If the function continues, he proved that it can be very close to the area of the region. So he said that if the function f of x is continuous on the interval from A to B, then, okay, then this sums, okay, is going to approach some fixed number, okay? It approaches A. Okay, that number we call the area of the function, area of the region. So as all the delta xi, okay, they all approach 0. Okay, when the subinterval is getting smaller and smaller, okay, uniformly, okay, I just say uniformly. Uniformly means the largest one approaches 0. The remaining of them all approach, right? Uniformly when the largest one approaches 0. Then the Riemann, this is called sum, right? Then They approaches fixed number, and that fixed number should be called the area of the function, area of the region. Okay. So there, so that's what he proved. Okay. We're going to check whether this is correct now. Okay. And so the limit, yeah, this approaches a finite number, unique. Okay. And this A is called the area of the region. Okay. Yeah. First of all, you know, the area, if it can be defined, can be approximated by those sums. Okay, finite sums. And Riemann shows that if the function continues, then those sums approach some number. Okay, that number should be called the area of the region. Okay, and yeah, the proof is pretty abstract. Okay? Riemann is a German mathematician. My opinion, the modern science, okay, especially in mathematics, were created, yeah, by German mathematicians. Okay, like the famous mathematician Gauss, you know. Okay, Riemann is after Gauss. Okay, there are many mathematicians actually. There are many. Most in geometry actually come from Germany. Okay, then spread to France, then to United States. Okay, United States actually is after World War II. Okay, there are some scientists, yeah, moved to United States, including Albert Einstein. He's Jewish, but he actually was in Germany. Okay, can you see that, right? And yeah, there. I think that during World War II, it's a very interesting story. The scientists can be very easily moved to United States. That it's very easy for them to get a visa. Okay, even some people without the visa, I still remember that Albert Einstein's co-work and his wife with kids that can just have a picture with Albert Einstein that can pass the test, and they got the visa immediately. That's it. That was the early days. Okay. Anyway, so that's why. Yeah. Anyway, German the science is very good, even right now. That's my opinion. Like manufacturing, for example, we have to say that like that. Okay. All right, so let's look at this and let's check some examples. Before we do examples, I have to recall some formulas. Okay, we need the following formulas. Okay, the first formula is 1 plus 2 plus 3 all the way to the end. It's n times n plus 1 divided by 2. Okay. I think a majority of students know this formula. The second formula is 1 squared plus 2 squared plus 3 squared. Okay, it's going to be n times n plus 1, looks very similar, right? And this divided by 2, right? Actually, I'm going to write it in this way, 2n plus 1. Okay, so this is additional term, okay? 2n plus 1. So sometimes we just simply write divide by 6. 2 times 3 is 6. Then the third one, even more strange. Right? It is going to be squared. Right? We mathematicians do not create formulas. They just discover those relationship. Okay, it's already given by the God. Okay, that's why many scientists finally just believe the God. Okay, because they just discover whatever is already created by the God. Okay, not just make the formulas. So you can check that. Okay, let's check, verify the last one. Okay, 1 cubed plus 2 cubed, right? It's gonna be 8 because 1 plus 8 is 8. 1 plus 9, 8. That's a 9. 9 is a 3 squared. Okay, 3 is 1 plus 2. Okay, cool. Okay, so then 1 cube plus 2 cube is going to be, it's always perfect square. It's 1 plus 8 plus, 3 cube. 3 cube is 27. So that is going to be 36, right? 36 is 6 square. 6 is 1 plus 2 plus 3. You see that, right? So maybe the guy who discovered that formula at the very beginning, just we call it discover because you know create. Okay. So maybe look at the first 3 examples, then say maybe this is true in general, you know, then trying to prove it. Prove it, maybe he couldn't do it, then he made a conjecture. But other people who are very good in math, they probably can prove it. Okay. So this is the formulas we need. Right. Then let's look at the example. Okay. I'm going to use a Riemann's idea to verify his formula. Okay. I look at the triangle. It's y equals 2x. Okay. And here's 1, here's 2. Because this is a region, right? I know that this is a special trapezoid. So the area, I already know that the area by the formula. It's right. It's this side is 1, 2. This side is 4. So 2 plus 4 divided by 2 times the height. It's going to be 3. Okay. All right. 3 is the area. Okay. Because it's trapezoid. We know we know how to use the area formula to find the area formula for the trapezoid. But let's try to use a new Riemann's idea. If we are able to use a sequence of the we call Riemann sums to get the limit, then the limit should be equal to 3. Okay. So the idea is the area also should be equal to the limit of Riemann sum okay. Okay. Each Riemann sum represents the area of those rectangles. Okay. How can I do that? I choose a special one. Let's look at okay. X. I'm going to divide the interval from 1 to 2 into n equal parts. That's called delta x. 2 minus 1 over n. It's n over 1. So yeah.
So is it x such group I? What is the orders please? I just got
X.
Yeah, so
it's a 2x, right? Y equals 2x, and here this is a formula. Approaches infinity, n approaches infinity. This is n, is a sum of n terms, and yeah, x star is the sum number. Okay, so x star is an arbitrary point in the interval. Here's xi minus 1 xi, somewhere here xi star. Okay, arbitrary point. But we are going to choose a special because otherwise we don't know how to even find the limit. So xi is going to be 1 plus I delta x, okay, which is 1 plus I over n. Then you can check that when I equals n, that's 2, okay. So you get x0, which is 1 less than x1 less than x2, xn, that's going to be 2, okay. And the delta xi, which is xi minus 1, is just nothing, just delta x, the same. And I can take xi star to be any of the number. I'm going to decide to use xi, okay? It's not necessary to be, yeah, just arbitrary point. So I take the left hand point, right hand point, which is 1 plus I over n, okay? So let's look at the Riemann sum. The Riemann sum in this case is f of xi delta x, right? And f of x is 2x. So actually it's 2xi times delta x. Okay, I'm going to put the details here. What is 2? Xi is 1 plus I over n. Delta x is 1 over n. I claim that this is going to approach the area of the region. Okay, it has a limit. Okay, how can I simplify this? So this is going to be, there are two terms here. It's going to be 2 over n, 2i over n squared. And if you separate them, you can separate them. It's n over 2 plus n over 2 over n and 2 over n. So you have n terms. Then you have n squared 2 times 1, n squared 2 times 2, n squared 2 times n. Okay. So the first term, you have 2 over n times n, you have n terms. The second one, you have to take 2 over n squared out. It's 1 plus 2 all the way to n. And then we simplify it. You get n times n plus 1. And these two cancel out. So you will get n over this, n plus 1 over n. All right. It approaches 2 plus 1, which is 3. You see, 3 is the area. Yeah, we find out, at least we show that this is going to be 3. Okay. And that is going to be the area of the trapezoid. We already know that. But suppose we don't know, that's how do we calculate. Okay, we only know the formula as we know, we just know the definition of the area of the rectangle, right? And we use the rectangles to approximate an arbitrary region. And you get Riemann sums, then you take a limit. And Riemann says a limit definitely, yeah, must exist. And then the limit is going to be the area of the region. That's the idea. But not always we can evaluate the limit, okay? I'm very curious about parabola. Okay. This is a parabola, right? Y equals 1 minus x squared. I'm really very curious about the region of this. This is not a part of the circle. Are we able to find the area? Okay. This time we don't have any formulas. Find the area using Riemann sums. Okay. The area is going to be the limit of the Riemann sums. Each Riemann sum is an approximation of the area. Okay. Riemann says that limit exists. All right. So the idea is you partition this, and you can use the left endpoint, right hand doesn't matter. Okay. So this is a small piece. So first of all, divide it. It's going to be 2 over n. Okay, divide the whole interval from -1 to +1 divided by n. So 2 of n. Then you partition the points -1 plus I delta x, -1 plus 2 n I. Okay, so those are the stem partition. This is the x0 and this is the xi minus 1 xi. Okay, and I also use the x star to be xi. Okay, you can choose the right endpoint. So I choose a very special partition of the interval of all the subintervals I have equal side. I also choose the point in each subinterval as the right endpoint. Okay. Then I consider the Riemann sum. The Riemann sums, okay, should, yeah, this is a Riemann sum, the special Riemann sum. The geometry mean of this Riemann sum as the area of this rectangle. Okay, look at that, right? As the area, the total area of this rectangles, I to show you in the picture. Okay, I'm pretty sure. Look at the picture, right? Yeah, but I'm not sure this is larger than the actual area or smaller than the actual area. Okay, because on the right hand side, look at the rectangle. It's going to be underestimate the region, right? Because the product f of x times delta x is the area of the rectangle, but that rectangle does not cover the whole region. So they underestimate the area of the region. But for the rectangles on the left hand side, they overestimate. Maybe that cancel, right? But anyway, so there's error between the actual area and the Riemann sum. But Riemann says that the error is getting smaller and smaller if you take the limit. That's his work. That's why we call those sums Riemann sums. Okay, we give him a credit. So Riemann passed away at the age of 40, but he did a very good work in many areas. On the internet, if you type Riemannian geometry, and you have to find out the millions of web pages about this. Okay, and Albert Einstein learned the Riemannian geometry, so he can use that language to finish his paper on general relativity theory. Okay, without Riemann's work, Albert Einstein cannot finish his job. Okay, work. Okay, so mathematics can be used as some efficient language to. You need a language to describe any sums. Okay, do the computations. So the geometry, okay, created by Riemann, is used by Albert Einstein to describe the general relativity theory. So here's the point. In science, many discovery, so it's actually in the interdisciplinary area. Okay, so if you learn lots of things and focus on something in the future, probably can do better than the people who only focus on that area. Like even computer science. If you get a degree in computer science, but almost all the courses you take is just programming. Okay, so you will become only ordinary programmer. Okay, but your background, if you get a master's degree in geometry from math department, then you switch to computer science. You probably can do excellent research in the imaging process, and you have lots of projects from medical school about imaging process. Okay, so otherwise you have to talk to somebody else. Then it's harder to find somebody else can communicate with you when you're trying to write programs. for imaging process. You have to be the expert in the area too. Okay, so that's why it's interdisciplinary area. You can become more successful. Yeah, like a data, bigger data, right? What do you have to study? Bigger data, right? If you want to study, right? That involves lots of things. Okay. Right. So, all right. So let's the Riemann sums, and we calculate the Riemann sums. I'm very curious about the area of this portion of the parabola, right? So let's see. So the Riemann sum is going to be f of xi is 1 minus xi squared, right? And the delta x. That's the first step. Then let's put the details. 1 minus xi is going to be -1 plus 2i over n squared. Well, it's not as simple. Okay. Then you get this. So what am I going to do? Can I find the limit? Because the limit is going to give you the area. Riemann already tells you that the limit exists, and this should be the area of the region. All right, so let's simplify a little bit. We have to simplify it. It's 1 minus 1 minus 4i over n plus 4i squared over n squared. Okay, step by step. We are not in big hurry. 1 minus 1 is gone. 4i n minus 4i squared over n. Okay, not too bad. And then I multiply this out 2 times 4 times 2, right? It's going to be 8. So n squared. This is going to be 8 over n squared I. And this is going to be 8 n squared I squared. Oh, this is already square here, so it's cube. Whoa. Okay. Then what is the sum of I? I from 1 to n, 1 plus 2 plus 3, right? So it's 8 over n squared, n times n plus 1 divided by 2. Here's 8 over n cubed. So the sum of I squared is 1 squared plus 2 squared plus 3 squared all the way to n squared, which is going to be n times n plus 1, 2n plus 1 over 6. Okay. I want to find the limit of this. Okay. So let's simplify. It's 4. N over n is gone. It's 1 plus 1 over n. That's the first part. Then 8 of, it's a 4 over 3. Okay. And n is gone, so it's 1 plus 1 over n. 2 plus 1 over n. Okay. If you simplify a little bit. So when n approaches infinity, this has a limit because 1 over n approaches 0. So it's clearly when n approaches infinity, it's a 4 minus 4 over 3 times 1 times 2. Okay, it's going to be 4 minus 8 over 3. 4 minus 8 over 3. Okay, it's going to be 12 minus 8. 12 minus 8 is 4. All right, so it's surprised it's going to be 4 over 3. Okay, now, is this a reasonable answer? Because when you get an answer, maybe the computation mistakes there. I want to see if it's a 4 over 3. It's a reasonable. Okay, this is a parabola, right? Here's a 1, here's a 1, here's 1. So I'm going to do some rough estimate. What is the possible area? I think the area should be smaller than the area of this rectangle, right? But also should be larger than this triangle, right? So we can give some estimate. Area is going to be greater than the area of the triangle. So the area of the triangle is half of 2 times 1, which is 1. Okay, less than the area of the rectangle. rectangle is just the base is 2, the height is 1, so it's 2. So area is between 1 and 2, and we got 4/3. Huh? That's reasonable. Makes sense. Okay, so the area of this parabola, we never learned this formula from, because we are not going to give a formula because there's so many different type of a parabola there, right? So you cannot give yeah. All right, so some reason. Okay. All right. So you can find a formula for the area of this portion of the parabola. Okay. Using Riemann's idea. Okay. Get a Riemann sum and blah blah blah. You know. Okay. And you will see that this is going to be 2 endpoints. It's going to be if set y to be 0, that's a b over a, the square of b over a, that's square b over a negative. Okay, then you divide them into n equal parts, and you can cover exactly do the same problem. Okay, and you get Riemann sums. Okay, so you get an area for that region. Yeah, one more problems we can. The next problem is find the area under the region y equals x cubed. Okay, x is between 0 and 1. Now, this is a point here, 1 and 1. So I can tell the area should be less than, right? Less than the area of the triangle, right? Right? So it should be less than 1/2. Okay. I cannot figure out the lower bound. Okay. To find this area, I use a partition x shape. So delta x is going to be 1 over n, and xi is going to be 0 plus I delta x. It's going to be in. Okay, so you get a bunch of points here, xi minus 1 xi, right? So the area should be equal to the limit as n approaching infinity, and f of xi, so I cubed delta x. Yes, this is a Riemann sum. If you look at the picture here, this Riemann sum is just the total area of this rectangle. So I think it's overestimated the area of the region if you look at this picture. Okay, but the limit still is going to be the area of the region and the graph. But for any given n, this partial sum, okay, is going to be it should be larger than the area of the region and the graph. Okay, so let's compute it. Okay. So xi, okay, so this is a formula, right? And you have n cubed, so n to the fourth power should be taken out. Okay. We already know the formula. It's 1 square, 1 cube is a 2 cube, right? So we know this formula. It's going to be squared, right? Now let's move n to the fourth power into the square. You will get, okay, then further simplification gives you, okay, so the limit is 1/4 as n approaches infinity. Okay, so 1/4 is the area of the region. Okay, so area is going to be 1/4. 1/4 is less than 1/2. All right, so that is the exact area of the region. And the y, when the curve y equals x cubed.